Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 59 today and we are discussing about adhesion on a rough adherent. This topic that we started discussing about in the last lecture has been taken from this paper by Fuller and Tabor, and today I will continue this discussion further from this particular paper by Persson, Tosati and some other papers as well. So, if you remember, in the last lecture we showed that when there are roughness in the adhesive and let us say a smooth spherical indenter is being brought in contact with a surface that is decorated with asperities. So, in that case, as the asperities height increases, the adhesion decreases. As a result, the pull of force that decreases. So, this is relative pull of force, that means actual pull of force divided by the pull of force when the surface is smooth. And this particular observation was attempted to be explained by considering that the surface consists of this kind of asperities. The asperities height vary from maybe according to a given functional form, and although the height varies, they have the same radius of curvature at the tip. So, this looks spherical there. And now these asperities are being this adherent, which is a smooth rigid adherent, that is being brought in contact with this adhesive having asperities. So, first this asperities contact and now you apply more load and then you pull it off. So, this is a frictionless contact that was considered and linear elastic deformation, and then the relation between the load and the displacement or the deformation of the asperity over and above their height was related by the JKR theory, and this relation is nothing but whatever you obtain from the JKR contact mechanics, and it was written in this particular form where this quantity psi is in the form of 1 plus p by pc, and so now you write p by pc as a function of delta by delta c. Now, delta c is the critical pull of distance of the asperity. So, remember that these asperities have different height, but their radius of curvature at the tip that remains constant. So, as a result, this delta c, which is a function of the work of adhesion at the surface and the radius of the asperity, radius of the sphere or the contacting body, and Pc is the critical pull of load, that also depends upon radius and work of adhesion and all that. So, these quantities they remain independent, okay, of the height of the asperity. So, now we will like to see that what to do with this and how that result can be used for measuring the or estimating the adhesion when there are, let us say, asperities or when you consider all the asperities. So, let us say there are n asperities per unit area. So, not all asperities are in contact with this adherent. So, the ones which are expected to be in contact with the smooth plane on the separation of the separation above the datum. So, basically the number of asperities which will be in contact, okay, with this surface over here, that can be written as, let us say, n is equal to, n is the total number of asperity and fraction of asperity having height z to z plus dz is phi z, okay, and then there are 0 to let us say infinity. So, there are all different kinds of asperities. So, it is not 0, it should be d, because the d is the gap between the datum of the surface and the top surface. So, basically these are the surface, this is the surface having this asperity, and then this is the contacting body. Let us say the contacting body is something like this. So, there are asperities which are not in contact, there are asperities which are in contact. So, we want to find out the number of asperities which are in contact with this contacting surface over here, and that fraction having height. So, here the height is d, and so the height of these asperities which of which the height is, let us say, z, which is greater than equal to d, only those asperities they will be in contact with the surface, right. So, the fraction of those asperities is given by this integral, and where phi z is the number of asperities having height having height z to z plus dz, height between z and z plus dz. So, it is like that. And so, the pressure that will be applied by these asperities can also be considered, the force exerted by all these asperities. So, let us say this is P, that will be equal to, let us say this is N and this is D to infinity. So, the pressure applied by those asperities having height is Pj, and this is the Pj, and this is Dj. So, the pressure applied by this asperity having height is small pj, and then this is pj and tj, like that. So, we can write in a dimensionless form where n into pc, okay, and it is pj by pc. So, this is the dimensionless form. Remember that we obtain the relation between p by pc, okay, and that is where it is useful, and then phi z can be given. This is the distribution function that is being considered. This is a Gaussian distribution function, height distribution function of these asperities. So, therefore, the force exerted by these asperities can be given as n, this is Pc here, and this goes from d to infinity, and this is P of z. So, I will write it in terms of this function, and this was delta by delta c, and why I change it, okay, that will also be clear in a minute. And here let us say this is sigma s, this is square root of 2 pi, and this is let me write it over here, yeah, I can write it here, exponential minus this is z square by 2 sigma s square, and this is dz. So, remember this sigma s is the standard deviation of this distribution. Okay. So, this shows that for the height variation, okay, between these asperities. So, that part it takes into account. So, we have this equation. Now, the question is that what should be the value of d. So, what happens is in the experiment that we bring in contact this particular because this is the asperity having this surface having asperities, and we have this adherent. So, this adherent plate is first brought in contact, and then it is pressed, okay, and then it is pulled off. So, it is first pressed and then it is pulled off. So, we can do this, we can find out that what is the deformation, okay, of the asperities. So, the initial height between this basically the gap between this contacting surface and the datum of this adhesive is let us say d, and so and the height it is d now, but the z is the height of the asperity. So, the deformation of the asperity can be written as delta is equal to z minus d, right. So, if the asperity height is z and d is the gap between them, so the deformation, okay, that can be written as delta. So, instead of having z, we can actually replace that in terms of delta. So, that will be, so therefore, this what will happen, this relation will be something like this, square root of 2 pi here, and this is let us say function of this is delta and delta c. So, we need to do it delta because here the function is in terms of delta, right. So, therefore, we need to change this variable from z to delta, that is what we are doing. And so, here d delta is equal to dz, that is straightforward, and here we write a minus instead of z, it is z is equal to delta plus d. So, delta plus d whole square by 2 sigma square, and this is d delta, like that. And we can do further. So, now the limits I have to say. So, the limits are at z is equal to d, delta is equal to 0, no deformation, and at z is equal to infinity, of course, this is infinity. So, the limit of this delta goes from 0 to infinity, that is very clear. And now we can write this delta and d in terms of this dimensionless form. So, delta as you remember, so that is the deformation, and then sigma s, it is the standard deviation of height of the asperity height. So, asperity height, right. So, we can write the dimensionless form of delta and d both in terms of this capital delta here and h here, and we can do that, and therefore by doing all that, okay, we get something like this, and here we will get therefore n, this is Pc by square root of 2 pi and 0 to infinity here, and this is function of, this is capital delta by this is delta c here, okay, and exponential, this is minus half and delta by sigma s, so that is capital delta plus d by sigma s, that is h here, and like that, and delta, this delta divided by this sigma s, that is capital delta. So, I write it in a dimensionless form completely, this equation. So, therefore, we have this pressure, expression of pressure now in terms of this. Now, what should be the lower limit? Okay. So, the lower limit is of course d, that is the separation that to begin with. Now, what happens is in the experiment, as I said, that you first have certain height initially, but then you try to press it. So, when you try to press it, more number of this asperities they come in contact. So, that particular matter has to be taken into account, right. So, because suppose you had pressed, you had just brought it in contact and then you have pulled it up. So, then in that case only few asperities will be in contact, okay. So, adhesion will be that much low. But let us say that now you apply some more amount of load, right, and then you try to bring it in contact, more number of asperities come in contact. So, let us say now the height decreases to d0 over here. So, since it is d0, so therefore, the lower limit has to be altered to d0. So, what we will do here then is p dash is equal to n, this is Pc sigma s square root of 2 pi, and this is instead of d I will have d0 here. Now, d0 and infinity, this is f of delta c and exponential minus, and remember that we are writing z is equal to delta plus d, right. So, delta plus d whole square by 2 sigma s square and d of delta. So, the delta when z is equal to d0. So, z is equal to delta plus d here. So, when z is equal to d0, that means the lower limit is d0. So, then the delta will be d0 minus d. So, it will be d0 minus delta, yeah. So, it is d0 minus d and it is infinity there, d0. So, d0 minus d, yes. So, that is the way I will come. So, now again we can non-dimensionalize it, which is fine. So, right. So, this is fine. So, now actually what happens is that lower limit kind of integration can be defined in another way, okay. So, why it is? Because let us say that initially only the tallest of this asperities that is in contact, okay. So, the tallest asperity remain in contact and now we press it. So, press it means more and more number of asperities that come in contact and then I pull it off. So, initially there is the tallest one that is going. So, therefore, the what is the minimum maximum deformation, okay, that of the tip that we can go to, okay, that is the thing, that is the idea. So, what it means is that the minimum height that will be there, minimum height asperity that will get in contact, okay, that will have the delta c, that is the maximum amount of deformation that it can have, pull of deformation that it can have, okay. So, the asperity of minimum height that can be touched will be what? Will be d minus delta c. Why? Because delta c is the maximum deformation of the tip, okay, that can be that is possible before the separation happens, okay, that is the pull of deformation that you can say. So, therefore, okay, when we find out, when you press this top adherent, okay, we will go up to, we can go up to this particular height, that is d minus delta c. So, the minimum, so when you go to d minus delta c, that is the minimum height that you can go, because once we start pulling it, then it is up to the delta d minus delta c height asperity that will come out of contact, okay, of this surface. So, that is the way. So, therefore, we can have our lower limit over here, that should be replaced not by d0 but d minus delta c. So, now it is be like that, and therefore, since delta is equal to z minus d, So therefore, writing z is equal to d minus d delta c, we have got this minus delta c. So the lower limit here, as you can see, it is minus delta c, and then of course you have done all the non-dimensionalization and all that, and that is the way it is. So actually we can have both d0, okay, and d minus d lambda delta c, whichever is lower, as the limit, because we should go to the lowest one, limit one, because then we can have the maximum number of asperities in contact. So that is the way it is. So once we have that, then we can of course use, we have to solve this equation and multiply it by this weighting factor and like that, and obtain this integration, and that we can, by that we can get this p dash. And when you do all that and we write p dash by NPC like this, we can get this kind of curve. So at load 0, of course no, that is the separation, minimum the initial separation, and then as we pull off this load, then of course the separation increases as we first decrease it and increase the separation, and separation increases, let us say, then the pull off load becomes more and more negative, and then at this minimum pull off load or maximum pull off load over here, that is negative, okay, we will have this separation that happens. Now as you can see here that this data for two different values of, let us say, sigma. So sigma, as I said, so that is the standard deviation of the height. So that means the that is the in the distribution, width of the distribution within that is what it is defined, takes into account. So in this case the width is larger, that width of the distribution is larger, okay. So therefore width of the distribution is larger here, right, width of distribution, okay, that is actually larger over here, and as a result the pull off force actually decreases with respect to this. So 0.13, okay, this is so this 0.13, so 0.13 here and 0.16 here. So therefore here the width is larger here, so therefore the pull off load here is actually lower with respect to this. So that comes out, so that observation comes out of this calculation. And also as you can see here that x axis here is sigma, so that is the width. So as sigma increases, okay, the pull off load that of course decreases, and as delta c increases, so the increase in delta c here means more and more stronger adhesion. So stronger adhesion means that it will go, pull off load will actually decrease like that. So this ratio sigma by delta c, that take into account the effect of this adhesion and also the roughness. So if this roughness means the width in the distribution of this asperities height. So as the asperities that width increases, so the pull off force decreases, and as delta c increases, that means adhesion increases, the pull off force decreases. Now that was okay, we could explain some of the observations, but it so happens the actual situation is not that simplistic, it is actually somewhat more complicated. So for example, like this particular experiment that was done by this Briggs and Briscoe 1977. So that shows that pull off load at a very small amplitude roughness actually increases. So it is not all the time it is decreasing, it is also increasing within some distance, within some range, and then decreases. And so this particular, or rather it is not pull off force, it is in terms of this effective work of adhesion. So that was spread. So a work of WA is that work of adhesion for the smooth surface, and W effective will be the one that is for this rough surface. So within a range of surface roughness, adhesion, okay, increases over on a smooth surface. That is what we see over here. So how do you explain that? So this effect more prominent for softer material. So what it means is that when you have got a rough surface, then naturally for a softer material, because of this adhesion has the tendency to come in complete contact. So that aspect needs to be taken into account. Furthermore, the surface topography consists of not just one length scale. So we have just here considered those asperities, but actually the surface has got all different length scales topography. For example, like it has got, let us say, from 10 to the power minus 2, that means a centimeter range feature, then millimeter range, micron range, then up to atomic range. So as a result, okay, this surface topography, okay, in this at this different length scale, that affects phenomena, okay, different phenomena. For example, like weightability, okay, will get affected by surfaces having nanometer range nanometer raised to micron range features, and let us say nucleation, okay, will get affected by even smaller features, okay, so almost sub nanometer level features. In between friction, adhesion, color, okay, all this gets affected by let us say nanometer to range to maybe tens of nanometer range feature, like that. So surface have got these different these features, topographical features, and that needs to be therefore looked into in the context of this adhesion that we are working here. Now how do you do it? So it seems that surface can be shown to have this kind of profile. So it has got different locations, a different amount of different height, like that, and a very simplistic way of describing this surface will be to obtain this average roughness. So average roughness is just find out the height and the average of that, and you can see that height is positive, negative both. So in some case it may show even surface adhesive average roughness to be 0, which is completely wrong, because surface is indeed not having 0, is not a smooth surface. So therefore the better way of doing it will be to obtain the RMS roughness, that is called the root mean square roughness. So root mean square roughness is what? You find out the magnitude of this height, and then you sum it up divided by the n average of that square, and then find out the square root of that. So this is the, and that way over here you are having 0 roughness, so that will be taken care of by this RMS roughness, you get a better picture. Now how good is this RMS roughness calculation or estimation good for our surface? Now what happens is that when you do this this RMS roughness, which we commonly do an average roughness, the average roughness of course does not make much sense. This RMS roughness when you do, okay, I will just show you in a minute that it is dominated by certain length scales, okay. It does not take into account all the different length scales, and does not contain the surface roughness information over many length scales, because okay, here I have just one scan of the surface, and in that scan I have this roughness, this height distribution, and from that we are obtaining, okay, this RMS roughness. So this scan that has been done at one length scale, okay. So for example, like if I had make the scan in this length scale, can I say this is completely smooth? Possibly no. In this case also, if I magnify, I will possibly see a surface like this. So what it means that the RMS roughness and this length scale will be actually different. And there are many other issues. For example, over here you have got like 3 different scans, line scan, and here if we try to see the RMS roughness, okay, for this surface, all the surfaces have the same RMS roughness. So here the RMS roughness is Q, here same all the cases, but actually these 3 surfaces are completely different. So for example, this surface A, okay, that is a superposition of 2 sine waves of different wavelengths, okay. So just superpose these 2 sine waves, it will give this profile, and the RMS roughness will be SQ, which will be same as the others. Now this is a capillary wave, another surface having another random roughness surface, and then here is a randomly rough surface, okay, which is another case. So these are all different length scales, a different type of surfaces, but having the same SQ, so that is the RMS roughness. And if you let us say here, instead of taking the whole range, if you take only this length, okay, you will see that RMS roughness will be now halved, different. So now a surface, okay, how can it have a different RMS roughness? So RMS roughness should not depend upon the range, okay, domain that I have taken, it should not depend upon that, okay. So like that. So therefore this RMS roughness, the way we are calculating or we are estimating this equation that we described, that possibly is not the more appropriate, there can be better way of doing it. So it seems that one can obtain what is known as this power spectral density, PSD. So I will describe in a minute what exactly this means. So one can obtain this power spectral density, and one can plot it with respect to Q, it is the wave number 2 pi by lambda, or like basically let us say if it is a time series, it will be frequency. So in amplitude versus frequency, we know that we can obtain it by Fourier transform of a signal, right. So very similar thing over here, this is a power spectral density in the y axis log scale, and here log of wave vector, that is Q, and that will give this kind of profile, these two picture. So now here you see, I told you that this particular surface A, it is a superposition of two sine waves. So naturally there are two wave vectors, okay. This is one wave vector and this is another wave vector, means wave of one particular wavelength, this is another wavelength, a summation of that gives rise to this particular surface profile. Over here the same kind of calculation will give you this kind of profile, where this is a almost like a curve, okay, like that. PSD of randomly rough non-self-affine frozen capillary wave surface, non-self-affine surface. So what is self-affine, I will come in a minute. And here this is a PSD of a self-affine surface with contribution from several wave vectors, means randomly rough. So it has got a summation of all different kinds wavelengths waves of different wavelengths, and as a result you have got okay, this surface, and when you do the PSD or power spectral density, you will get a plot something like this, where over this whole range of Q, that means this is one wavelength, this is another wavelength, so like all these wavelengths, right, and you obtain the power spectral, so that quantity called C log plot, and you all in log plot you will get a linear profile like this, and this is for one kind of slope, one particular surface, this is for another surface, and they have got different slope like that. So here the slope is higher, 0.8 here, and the slope is 0.3, so there are two different surfaces. So two surfaces with different, so this particular slope, this is called the Hurst exponent, okay, but identical RMS roughness. So that is the thing here. So the PSD of self-affine surface with contribution from several wave vectors, and here we present two different surfaces, okay, with these two different Hurst exponent. Now what is this self-affine fractal surface? So surface for which if we make a scale change appropriately different along the two directions, parallel and perpendicular, then the surface does not change its morphology. So I will just explain it something like this. So as I was telling you, the surfaces one particular magnification looks smooth, another magnification looks somewhat rough, and if you further magnify it, you will look more rough or like a different roughness. So roughness on many length scales, okay. So these are called fractals, and something like this. So suppose you have a height profile of an image, okay, which is given as z as a function of a z is equal to h of x y. Now you magnify the image by a factor m, let us say 10 times or 100 times, and then you try to see the surface, and if you do that and these are magnified, so okay, this z value, okay, will be something like this, m into h of x by m and y by m. So if you do that, so that means you multiply this height, okay, by this quantity m, you will get this particular value. So this means that once you multiply it by this m, okay, this surface at this length, at this magnification becomes identical as this surface, okay, at this magnification. So original and magnified image become indistinguishable. This image original and magnified image, that becomes indistinguishable. This kind of surface is called the self-similar surface, in which this is multiplied by m, linear. And when we have and for this surface, this is the kind of picture you will have. This is a fractal surface. So as you magnify more and more, the surface looks similar. So this is called a self-similar surface. And when you instead of m, you multiply it by m to the power h, okay, h is a quantity which is called the Hurst exponent, and normally it has the value between 0 to 1, okay, you have what is known as the self-affine surface. So now this original and magnified image becomes indistinguishable when you multiply not by m to the power a factor h, okay. So this particular constant is Hurst exponent, and so which value lies between 0 to 1, and since we are talking about two dimensional picture, we will have this fractal dimension df is equal to 3 minus h. Of course same calculation or same things can be done, okay, for a line, okay, that also can be done. So this is the way to characterize this surface, okay. So as I was telling you, so this surface, flat surface, okay, then it has got the rough surface with asperities, further magnify the asperities, and it look like that. So this is called a self-affine fractal surface, and we can obtain the statistical properties of this surface. So I will take it up in the next lecture. Thank you.